everyone, I'm Kiara McKenney on behalf of the Applied Technology Council. I'd like to welcome you to this webinar on FEMA P 2012, Assessing Seismic Performance of Buildings with Configuration Irregularities. This webinar is brought to you by the Applied Technology Council under a contract with FEMA, the Federal Emergency Management Agency. If you haven't already, you can download the handouts using the link in the chat. If you don't see the link yet, it will be provided again in a couple minutes. We know that many of you are interested in receiving professional development hours for your attendance today. For those who registered and attend the webinar, a certificate documenting professional development hours will be sent by email within 4 weeks automatically. If at any time during the webinar you have questions, please type them into the Q&A window that you can open from the Zoom control panel. We're planning to have a live question and answer session at the end of the webinar, so please submit your questions as you have them rather than waiting until the very end to submit them. We'll answer as many questions as we can, time permitting. If there are any questions that we aren't able to answer live, we do plan to provide written responses for as many as is practically feasible. I'd now like to turn it over to Christina Aronson from FEMA's Earthquake and Wind Programs Branch, who will provide a brief introduction to today's webinar. Christina, please go ahead.
Hello, my name is Christina Aronson. I'm a structural engineer at the Federal Emergency Management Agency's Earthquake and Wind Programs Branch. It's my pleasure to welcome you to today's webinar on assessing performance of buildings with configuration irregularities. A little bit of background, FEMA has the goal of reducing the ever-increasing costs that disasters inflict on our country. Addressing the risk presented by our population of existing buildings is, of course, the most effective way of reducing the cost of future disasters. As part of its responsibilities under the National Earthquake Hazard Reduction Program, NEHRP, it's a mouthful, FEMA is charged with supporting the investigation of seismic technical design issues, the development, publication, and dissemination of technical design and construction guidance products, and the support of design requirements in ASCE 7 on irregularities. The resulting publication, FEP 2012-2012 report was to inform and improve codes and standards so that structures with configuration irregularities have a similar level of safety against collapse during an earthquake as regular structures. Many of the findings in the report have been used and adopted by the 2020 NEHRP recommended seismic provisions for new buildings and other structures and ASCE 722. We hope you will find this webinar useful, and we encourage you to let us know if you have questions. We also want to thank Applied Technology and Council and Mike Valley for helping us deliver this session. Back to you, Kiara.
Thank you so much, Christina. So now let me tell you about your incredibly accomplished presenter today. Mike Valley is a principal at Magnuson Klemensic Associates. He was Project Technical Director for the development of FEMA P 2012, the report on which this webinar is based. Mike has over 30 years of experience managing complex projects involving new construction and renovation. He brings special expertise in seismic and foundation analysis and design, and he has been a key participant in the U.S. development of performance-based seismic design approaches. Mike frequently serves on committees and advisory panels to develop and write national engineering codes, standards, and guidelines. Mike was named Engineer of the Year by the Seattle chapter of the Structural Engineers Association of Washington in 2007, and he received the National Council of Structural Engineers Association's James M. DeLahey Award in 2008. I'd now like to turn the webinar over to Mike. Mike, please go ahead.
It's my pleasure to speak with you today about configuration irregularities. We're going to talk about, to manage your expectations, we're going to talk about what configuration irregularities are in the first place, why they're a concern to us, how they affect seismic performance, how they're treated in the U.S. codes and standards. And as we consider that, you'll see that there are triggers or definitions of these irregularities so that we all understand what we're speaking of. There are design consequences, maybe analysis, design, and detailing requirements associated with the existence of various irregularities. And there are ways that we can mitigate some of those irregularities that we'll talk about specific to each type. As we're doing so, you've already heard that the FEMA P 2012 project was addressing irregularities. So we're going to give you a little bit of background about that project. The way that we'll lay out our webinar here, we're going to have some background information on the subject. We'll talk about that FEMA P 2012 project in an overview sense. We'll then get into the meat and potatoes of this, where we're going to talk about modeling and analysis requirements because they're key to understanding and resolving structural irregularities. And we'll have specific examples on horizontal irregularities and vertical irregularities. To start, though, we want to get on the same page with you about what an irregularity is, at least as defined in this project. We really needed to focus our effort. There have been lots of observations in the past about how structural configuration can affect performance in earthquakes. So the definition that we settled on after careful consideration by the project team for an irregularity is an aspect of configuration that, if unaddressed, detrimentally affects the structure's performance during an earthquake, leading to an unacceptable reduction in collapse safety or increase in damage. And we're going to talk about some of those specific words that we crafted in order to manage the way that the project would go forward. There are concerns with configuration, and the performance concerns that we could have in order of priority, being the highest priority, is that there could be an increased potential for collapse. And we know that collapse of buildings leads to loss of life. And of course, there are economic considerations, but loss of life is one of our key societal concerns with earthquake performance. Configuration challenges can also produce increased damage in a building. And as we want to understand the configuration of a building and its expected performance, we need to have the right kind of analysis to capture the behaviors so that we understand the problem well. And so configuration can affect our choice of analysis methods. Just to set the table on this idea, this is not simply an academic issue. Irregularities can cause collapse in buildings. In fact, about half of the deaths in U.S. earthquakes since 1970 are due to the collapse of buildings. There are other causes of death, but collapse is the primary cause. And that could be due to unreinforced masonry buildings or non-ductile concrete buildings. Those are not the subject of today's discussion. But irregular buildings often have problems that lead to collapse and loss of life. That's not just a U.S. problem, it's a global problem. Of the deaths in the Kobe earthquake in 2005, most of the deaths were due to the collapse of buildings. And when we dig in and look at those collapse statistics and the performance that's associated with it, most often those collapses are associated with either soft or weak story irregularities, which may include the weak column, strong beam variant we'll talk about in more detail, and torsional irregularities. So those irregularity types are most often associated with collapse. So the project looked at the horizontal irregularities that are defined and ranked them in order of importance as they might relate to collapse. And on the right side, you'll see just some little plan view cartoons. You'll see similar cartoons later so that we can make sure that we understand what we're talking about. But in the case of horizontal irregularities, each of these is a plan. And if there is some twisting response in the building due to torsional stiffness or strength characteristics, there is a greater chance of collapse. For the out-of-plane offset irregularity, where the vertical elements of the seismic force resisting system don't extend from the top of the building all the way to the foundation, but there's some offset at one or more levels, that also can cause collapse because the fuse between those vertical elements can fail, and perhaps that was not anticipated by the designer. The way that diaphragms of a building are laid out and configured can cause problems. Local failures usually not a global collapse, but those local failures can also be dangerous. Reentrant corners, so where there's diaphragms, where there are separate wings in the diaphragm, they can respond dynamically out of sync with each other, and there can be increased damage. The other type of horizontal irregularity that has been defined in ASCE 7 for a long time is a non-parallel system. The idea is that the lateral systems cannot be readily transformed into two orthogonal systems. And if that's the case, you need to consider three-dimensional analysis. You can't separate the response in one direction from the other. That's really just an analysis problem, not a performance problem. And we'll talk about that some more. The vertical irregularities, now in this case, because we're looking at vertical irregularities, these are elevations or sections of buildings in each of the cartoons. And so we could have a weak story. So with respect to the stories above it and below it, that story has a much reduced strength. And we could get concentrated damage in that weak story, and that could lead to collapse, as it has in many earthquakes in the past. A soft story irregularity is not a question of how much strength there is there, it's a stiffness issue. And the softer or more flexible story can deform more, especially under dynamic loading, and that could produce collapse. For an in-plane discontinuity, the challenge is that vertical elements of the seismic force resisting system don't go from top of building to the foundation. There's some transfer of that load, some concentration of that load as it works its way down. And in the concentrated areas, they can have excessive damage that could lead to collapse again. The weak column, strong beam issue is a moment frame irregularity. The idea being that when you look at the joint of a moment frame, the beams and columns that frame into it, if the system prefers to have hinging in the columns, there's a greater chance that all of the columns in a single story could hinge. And if that's the case, then the story could collapse. And so that's of concern. Vertical geometric irregularity, the idea is a little qualitative. It's not so much quantitative. It's you can see it when you look at it, and you can see that there's some change in the dimensions of the seismic force resisting system that would make it have a non-uniform stiffness or strength. There may be a heavy story in the building, a heavy floor, and that's a weight or mass irregularity. The concern being you could concentrate inelastic response because of that non-uniform performance. Walls in buildings can have discontinuities in them for a number of reasons that we'll speak of in detail a little later. But the idea is if there are those discontinuities, they tend to be areas where the performance of the building is worse, where there's a concentration of damage, and that could cause problems. And we'll talk about a gravity-induced lateral demand. This is not characterized in US codes, but the idea is important and should be on your radar, especially given modern trends in architecture. The idea is that if the gravity loads cause lateral response, that needs to be considered in the design of the building for its seismic system. So with that background on what are horizontal and vertical irregularities and some cartoons to maybe help you understand what they are, let's talk a little bit about the ATC 123 project that led to the publication of FEMA P2012. So this was funded by the Federal Emergency Management Agency, and the project was managed by the Applied Technology Council, who's hosting this webinar today. We did the work primarily in 2015 through 18. You'll see on the next slide some key participants. As most Applied Technology Council projects, this was laid out with a project technical committee with a large supporting cast of other researchers and engineers, and then there was a project review panel so that the findings were well vetted, and so that even the course of the project was directed so that it could be most useful. So the objective of this project that FEMA sponsored was to look at irregularity related design requirements in US codes and standards, as specifically as they appear in the NERP recommended seismic provisions, which then make their way into ASCE 7's seismic provisions. In some cases, the US codes and standards we have for existing buildings, ASCE 41 addresses existing buildings. And some of our material standards like ACI 318 and AISC 341 address aspects of configuration that are specific to their material of interest. So the notion is that configuration is important to all of us. The way that it's dealt with is across this family of products. And the goal of this project was to compare the performance of buildings with irregularities to the performance of buildings that don't have those irregularities, and see what we could do to level the playing field of performance. What can we do so that configuration irregularities, which can't always be avoided, what can we do so that those configuration irregularities don't lead to poor performance? And rather than simply qualitatively discussing the issue, the project was specific in that we wanted to quantitatively evaluate these aspects, so that although our past observations of performance have been qualitative in many cases, if we could actually quantify the issues, we could do a better job of getting consistency in the level of performance. And that meant that the quantitative consideration was looking at current building code triggers, and then thinking about how irregularities affect seismic performance and specifically collapse. And then we can measure code provisions to see how effective they are in fixing the problem or in improving performance. That really was the goal. The way that the project approached this was to do a literature review first, understand what has gone before, how the US and international codes and standards and guidelines address configuration, look at the research that's available, consider the observations in past earthquakes, and think about what the greater structural community has considered to be irregularities. What are the metrics and triggers that have been used? What kind of analysis methods can be used in order to do the quantification that the project aimed for? So we did some literature review. Then we chose the irregularities that we wanted to study. We'll talk about why we chose the ones we did. And then we had to embark on this quantification of irregularities and their effects on seismic performance. And we'll give you just a little background on how the project did just that. So this slide represents the irregularities that the project had on our radar. And the ones that are in gray, H6 and V6 through V8, are not in ASCE 7. They're in some other documents. So they may be in another US code or standard like ASCE 41. They may not even be in US codes at all, like the gravity-induced lateral demand. It's treated in the Canadian Building Code, but not in the US code. So this was casting our net wide, the range of configuration issues that we decided to approach. And then we needed to choose what we were going to focus on. I mentioned that there was a desire not just to have a room full of experts chatting about what they think is the case or what's important, but to look for opportunities to quantify the triggers and the metrics that describe them, and to quantify how we can address irregularities. And so that made us focus on some irregularities that already had a way to be quantified. For instance, you see on the screen, torsional stiffness irregularities can be quantified, and they're the way that we understand whether we do or don't have that irregularity. Similarly, with weak story irregularities, there are strength metrics that can be used in order to help us identify and then perhaps address the irregularity. So what our project focus was yes, quantifying things, but going back to our definition of irregularity, we wanted to look at aspects of configuration that could detrimentally affect the structure's performance. So it's not just an interesting aspect of its behavior, but something that could cause the behavior to be worsened, with a particular focus on collapse safety. We do include increase in damage as a concern. That's a reality, that's practical, but the higher priority is to try to address collapse safety. And so that meant that the ATC 123 project that led to FEMA P 2012 now had our focus of issues. An example of some of the things that didn't get considerable study include the non-parallel system irregularity, because there's no reason to think that a structure behaves poorly simply because the lateral system is complex or it's not orthogonal. Frankly, earthquakes always shake buildings in all three dimensions, and so the fact that the systems are not laid out so that, say, north, south, and east, west response are somehow definable separately doesn't mean that the building will perform badly. Similarly, things like reentrant corners can cause increased damage and should be addressed as a result, but they rarely cause collapse. And so we could take off the table detailed assessments of those kinds of irregularity. So then the way that we approached our work with a focus on collapse was to identify the structural irregularities that we wanted to focus on. We talked about how we selected those, to pick seismic force resisting systems that we could use to specifically analyze those configuration issues, then to design those baseline systems without irregularities, so to design regular systems, and then introduce irregularities and redesign and analyze those irregular structures and understand the degree of irregularity. And for all of those studies, we used the FEMA P695 method to assess the collapse safety of the building. We'll give you, you could have a day's worth of seminar on the P695 method. We don't have time, we have one slide. So I'll try to describe to you the way that the system works. The goal of this method is to simulate collapse using nonlinear dynamic response history analysis. And so you have to come up with a characterization of the building, a model, and include in that modeling the nonlinear behavior of the system. That's used to determine post-yield displacement capacities, and then you perform incremental dynamic analysis. In a sense, you are shaking this model with larger and larger earthquakes to understand when it collapses, what causes collapse, and to determine what its margin against collapse is when it's been designed properly. Because the reality is you can always shake something hard enough to cause collapse. It's just a question of when and how much that deviates from the design target. So that method is used in order to better understand collapse. The project wanted to have broad application across the US. And of course, to that same degree, it could have application worldwide to the degree that the types of construction are similar. So we looked at high seismic demands, seismic design category D, and we looked at lower seismic demands, so not zero. That would be a trivial exercise, but seismic design category B. We wanted to think about seismic force resisting systems that had either special or ordinary detailing so that we can understand the differences, the sensitivities of those systems to the configuration changes. We looked at low to mid-rise structures for the horizontal irregularities. We looked at mid to high-rise structures for the vertical irregularities. We thought about the range of analysis methods at our disposal in ASCE 7, specifically the equivalent lateral force procedure, which is a static method with linear modeling. We looked at the modal response spectrum analysis procedure, and we used nonlinear response history analysis for our assessments. You are permitted to use nonlinear response history analysis in design. That wasn't the way that we approached the design because that's not the most common. Usually the linear methods are used for design and nonlinear analysis may be used to prove out performance. We looked at high to low gravity loading, and for the degree of irregularity, as I mentioned, we selected first regular baselines, and then we looked at making them more and more irregular with a certain classification of irregularity until they were highly irregular, so that we can understand the range of response. So what we have here is, again, it's a listing of the horizontal configuration issues that were considered in the project. And what you see highlighted in yellow are metrics that were later modified as a result of this project. And most of the requirements that we see here appear in ASCE 7, which is used for new buildings. Some of the requirements appear in ASC 4117. Then for the vertical irregularities, we did the same thing. We've got this whole suite of configuration issues that we identified. The ones in yellow are areas where this project resulted in specific quantitative changes in ASCE 7. The ones highlighted in cyan were also changed in ASCE 722, but as a result of other studies. We'll mention it as we continue. And so then the way that these irregularities were considered in the ATC 123 project that led to FEMA P2012, you see here, you see that we focused on certain irregularities, and we had a number of different building types in terms of material and building heights that we addressed. All the details there are in the document. So this brings us to our first poll.
Great, so I'm launching it. So this poll is, which irregularity or irregularities are associated with an increased risk of collapse? Non-parallel system, reentrant corner, soft story, torsional stiffness or strength, weak story. And then there are a couple options that allow you to pick multiple. So just be aware that the first few options are, you're saying just that irregularity. So then we have non-parallel system, reentrant corner, and weight irregularity. You can also choose soft story, torsional stiffness or strength, and weak story. There's also the option to say that all of the above or none of the above. And this is, I know this is a bit of a long poll, so we'll give you some time to think about it and get your responses in. It looks like so far about half of the people have responded. All right, I'm going to go ahead and close the poll in a few seconds, so do your best to get a response in. And it looks like about 3/4 of people have responded. So Mike, I'm going to go ahead and end the poll and share the results. Are you able to see them?
Yes.
Great. So it looks like most people have responded all of the above, or they've selected the option with soft story, torsional, and weak story.
Right. So since our focus here is on an increased risk of collapse, most of you selected the correct option, 39%, that it is soft story, weak story, or torsional irregularities that tend to lead to collapse. The other things may matter, and some of them are still defined in our document, but non-parallel system and reentrant corner irregularities don't cause buildings to collapse generally. And the mass or stiffness irregularity also does not cause buildings to collapse. We'll talk about that more as we go on.
Great, Mike. I'll go ahead and close the poll.
So this final slide sort of summarizes what we learned from the FEMA P2012 project, borne out by other studies as well. An interesting finding is that if you use the modal response spectrum analysis method, which we have traditionally thought of as a superior method, a more precise or more accurate method than ELF, your buildings actually have a higher probability of collapse. And you might think of it that way because if the ELF design is more conservative, if it has greater strength and stiffness than the response spectrum analysis designed building, you should expect that it has better performance. Gravity-induced lateral demands are important in system performance, but as long as you consider the effect that the gravity demands have on your performance, you'll not have worse performance. If you ignore the fact that you have sloping columns or that you have sustained lateral effects, you will end up with a poor design. For torsional irregularity, we found that it is good to consider strength. ASCE 7 previously had not considered strength, only stiffness. We found that considering strength was important. If we use the orthogonal combinations, they can help us if there are torsional irregularities. Because the ELF method is more conservative than modal response spectrum analysis, we found that we could allow the use of ELF. It didn't need to be prohibited. And in fact, with modal response spectrum analysis, there are some options that you could use that would actually cause problems in your assessment of accidental torsion. We'll talk about that, but the project found that. We also suggested that the P delta requirements in ASCE 7 should also be related to some P theta requirements. That may be a new term to you. We'll talk about it in detail. Because the ELF is conservative and already we're required to accurately model mass, we really don't need to have a defined irregularity for mass irregularity or weight irregularity. The design can, as long as it considers the real weights and masses and the real strength and stiffness, the design can be adequate. We found places where the diaphragm design requirements needed to be clarified because the scope of the mitigation far exceeded the scope of the irregularity. And we made some minor adjustments to the triggering dimensions for reentrant corner and diaphragm discontinuity, based not on new studies, but by looking back at the considerations that were made when they were codified in the first place. That's going to take us into this next section where we're going to start to think in more detail about the technical aspects of our designs. So the idea here is that we have modeling and analysis requirements set forth in ASCE 722, as we have in earlier editions of the document. We're going to talk about some of the requirements that were removed in ASCE 722, and we're going to discuss the significance of the modeling requirements. So why is it's so important to be careful in your modeling of your structures? Where are the places to focus? And so that you don't get into trouble, or so that you can find problems before they occur in the field. And then related to that, there are specific requirements in ASCE 722 that we're going to step through so that we can understand how they help us to understand structural configuration and to make sure that structural configuration is treated properly. So just as a piece of background to perform structural analysis in increasing degrees of complexity, the simplest method is the equivalent lateral force procedure, ELF. We use a linear analysis and we apply static lateral loads. And those loads have been historically defined so that we can try to get not necessarily the true set of loads in a building, but a reasonable envelope of demands in a building that are suitable for use in design. That analysis method can be used two-dimensionally or three-dimensionally, but it's our simplest tool. Modal response spectrum analysis takes that same model or models perhaps and does something different. We still consider the structure to behave linearly, so using linear elastic analysis, but then we think about some dynamic response in a modal sense. That method can only be done three-dimensionally, so we can't use two-dimensional characterizations of our structure to use this method. The next step up would be to use linear response history analysis, where we actually select suites of ground motions. The idea is that we're trying to even better understand the dynamic response. So instead of characterizing the demands with a simple response spectrum, we actually think about specific ground motions. It's still a linear analysis though, and it's three-dimensional. And sort of the greatest tool, strongest tool at our disposal for practical structural engineering is the nonlinear response history analysis method. So that method uses ground motions to characterize demands and considers the inelastic response of a building. So nonlinear modeling. Again, this is a three-dimensional method. To understand the ideas here, we want to remember the reality that we're just trying to quantify. We're trying to take a mathematical look at some realities. And the reality is that earthquakes are always dynamic. The response is always dynamic. Our approach to design in the US and in most countries uses R factors or some other similar method to say that effectively we can't afford to design everything to remain perfectly linearly elastic for the greatest magnitude of earthquake that could possibly occur. Instead, we accept societally and then professionally that we could have some inelastic performance, some inelastic behavior, as long as we don't have collapse and as long as we don't have too great an impact on life safety. Perhaps we think about level of damage as well, but we use a shorthand method to get there. Instead of, in our typical designs, instead of using explicit nonlinear characterizations, we use R factors for systems that have been qualified for a certain degree of inelastic response. We know that nonlinear response history analysis is always permitted. It probably gives us the best shot at understanding the true nonlinear dynamic behavior, but it's not practical in 2023 to use that method for every building design. Now, you could expect that linear dynamic methods are better than the equivalent lateral force procedure because they're more complex. They include an explicit characterization of the dynamic response of the building. But in fact, that proves not to be true. It's possible, in fact, you noticed what the NERP Provisions 2020 report says, that the ELF provides more consistent story shear, overturning moment, and story drift results than modal response spectrum analysis. So when you compare the gold standard, let's say, of nonlinear response history analysis, story forces and overturning moments and drifts, to modal response spectrum analysis, and then you compare it to the ELF envelope results probably do a better job of capturing that nonlinear response. And so that means that in ASC 722, a change was made that allows the equivalent lateral force procedure without limitations for structures that don't have seismic isolation or damping systems. And where there are those other systems, there are some limitations, but ELF is still permitted. The caveat here is this study and other studies do find the ELF to be conservative, but you probably could somehow dream up a building where modal response spectrum analysis could identify something that ELF misses. And so there's just that caveat kind of hanging out there. We're not suggesting that you stop using modal response spectrum analysis, but know that it is less conservative than ELF. So irregularity requirements that were changed in ASC 722, based on the findings of the project that we're discussing today, the weight or mass irregularity was removed. It's no longer an irregularity as defined in the code. And ELF is permitted for systems with torsional irregularity. Since we studied that very carefully and we found that the ELF designs behave at least as well as the modal response spectrum analysis designs. And so the consequence that was in the code previously requiring that you use modal analysis was counterproductive. So we took away that prohibition. The Building Seismic Safety Council, PUC Issue Team 3, which develops the NERP recommended provisions which feed into ASCE 7, they did some of their own studies in parallel with what we were doing on our study. And they found that ELF could be permitted for systems with a soft story or vertical geometric irregularity. So the prohibitions on ELF were removed there as well, primarily due to the conservatism of the ELF method. So now let's talk about the significance of the modeling requirements that you do find in ASC 722. There's a reason that each of those requirements exists. Frankly, there's a reason that each word in each of those requirements exists. We're not going to read it together carefully word by word, but we will draw your attention to some important considerations. We do have to think about story displacements and drifts. We need to identify design forces for members. That's just part of our design process. And that means that we don't just build buildings and then put them on a shake table and test them. The reality is that we need some mathematical models in order to understand what we can anticipate. We already mentioned that the most accurate analytical model would be three-dimensional. It would include all the sources of stiffness in both the structure and the foundation system. It would include P delta effects. It would allow nonlinear inelastic behavior in the entire system so that you could to the best of our knowledge today, identify exactly how this would perform for a given ground motion, and then maybe consider a very wide range of ground motions. But the reality is that we have to design not just one building in our career, but we need to be able to design many. And as a society, we need to be able to accommodate construction and growth, but do so safely. And so there are some simplifications that we can make. We'll talk about those as we go. So there's a requirement in ASCE 7 that you have to think about the spatial distribution of mass and stiffness. Now, this is true whether you're thinking about it horizontally and plan on the left side of the page. You do need to think about where the center of mass is. You need to think about the resistance. You need to think about the flexibility of the system, and then also vertically in elevation. So for instance, you see that you have to think about where masses are greater at one story than at others, maybe where stories are taller, where the system changes so it's non-uniform. Perhaps there's weaknesses introduced because of the reality of having door openings or something like that. But the code requires that our mathematical model has to consider these aspects of the configuration. Another aspect of that you, I hope, are familiar with if you're a structural engineer, it is still common practice that we may have models, mathematical models of our building where the lateral response of that building is assessed separately from the gravity response of the building. And if that's the case, we need to make sure that we have an appropriate characterization of the gravity effects as they impact the lateral system. So this is the classic P delta effect. You see a frame at the top, and then if you wanted to analyze that frame only using the lateral elements, which are shown in red, you would need to consider how the rest of the system leans on that lateral system, so that as the building leans over and there's a total gravity effect, let's call it P, and it acts through a displacement delta, that tends to soften the building. It's a geometric reduction in the stiffness of the building. If you ignore that, your results are unconservative and you can have problems with behavior. So this is one that you probably have heard about. Maybe you consider it carefully in your designs already. A related issue can be called the P theta effect. And in this image, imagine that this building has not translated laterally, but it has some torsional response. And of course, buildings have real torsional response due to the way that earthquake motions hit the building. So even if the center of mass of the building hasn't moved in plan, the perimeter of the building and the gravity loads at the perimeter are being displaced. And that can cause the twist to be amplified. So that's a P effect, a gravity effect on the system going through an angle theta. And that's the name of this. So that's the idea that we can get lateral twisting response out of a system, even if it didn't move translationally. Another aspect of the distribution of mass and stiffness, and perhaps of forces, is the idea of a gravity-induced lateral demand. So I will say that the project, the P2012 project, suggested that a change be made to ASCE 722 to specifically identify this issue. The ASCE 7 committee chose not to make that change. We'll see if they make it in 2028. But the idea embodied in this is related to the distribution of mass and stiffness and of loads. So in the cartoon, you see the idea that if we have a bunch of columns at one story that all slope in the same direction, when you apply the gravity loads on the structure above, you get a net shear in that story. And that shear exists whether there's an earthquake or not, whether the wind is blowing or not. There's a preferred direction of movement in this building, and it's already under a lateral load even when nothing else is happening. And we find that it's important to consider that effect because on the one hand, you could say that it uses up some of the lateral capacity of your system. It also would tend to make the system want to move in a preferred direction. And so that's an important issue of distribution of mass and stiffness. ASCE 722 identifies where three-dimensional analysis is required. And the big idea is if in plan you could get coupling in the two directions, then you need to consider a 3D analysis or else you'll miss that coupling. So that's true for torsional systems, out-of-plane offsets, and non-parallel systems. There are detailed requirements related to diaphragm modeling. ASCE 722, the big idea is the first bullet. The structural analysis shall consider the relative stiffnesses of diaphragms and the vertical elements of the sizing force or existing system. So we can't think about the vertical elements in isolation. We need to think about how the diaphragms tie them together and how those various stiffnesses interact. But we mentioned before that although structural analysis and seismic response may be a complex problem, there are ways that we can simplify it at times. So there are some rules that you can apply without supporting calculations to decide that the diaphragm is flexible, infinitely flexible, and so load should be distributed on a tributary area basis. There are some other rules that say you can consider this diaphragm to be rigid without any calculations, infinitely rigid for the sake of your design. You also could do some calculations of the diaphragm condition to understand whether it seems relatively rigid. The code identifies that. If you can't put it into one of these categories, you have to actually consider the diaphragm stiffness explicitly because it has an impact on the way that the system performs. So some examples of that, if we've got part of one level has effectively a rigid diaphragm and another part of that same level has a flexible diaphragm, there's no simple mathematical way to describe those differences, and we would need to think about the actual stiffness of the diaphragm explicitly. If you have very large openings in a diaphragm, it can lead to diaphragm performance that could be mischaracterized if you treated it as rigid. Where you have outer plane offsets, as you see on the bottom left, the diaphragm at that level where the wall above and the wall below connect to the same diaphragm, that diaphragm is subject to greatly increased forces. And so you need to understand the stiffness and strength of the diaphragm to characterize the problem correctly. And then if you have what the code identifies as a reentrant corner condition where it's got some triggers, it doesn't have to be just a tiny corner, but if it's big enough that you end up with wings of a building that could behave dynamically independently of one another, you'd need to think about the diaphragm stiffness. And where you have a non-parallel system, you're counting on the diaphragm to get the three-dimensional behavior to work. And so you need to think about that diaphragm stiffness as it relates. So then for dynamic analysis, I mentioned before that the prohibition on ELF was removed because we find that more conservative ELF analysis actually produces results that are more consistent with the true dynamic inelastic response than the modal method would suggest. And so we're allowed without limitation to use ELF unless we have seismic isolation or damping systems, and those systems allow ELF with some additional requirements. I again note the caveat, although modal response spectrum analysis is generally less conservative than ELF, it may be possible that there's some strange distribution, and so the commentary cheats a little bit and says you may still need to think about that modal response. Because earthquakes happen not just in one direction or two directions, they happen across all directions. It's important to think about those two directions or the multiple directions. Again, the basic statement is that you have to think about an earthquake coming from any direction, but we've got some simple methods to get us there. If we're doing ground motions, we use two-dimensional ground motions. That's automatic. If we're doing other linear methods like ELF and modal response spectrum analysis, we have some rules that allow us to combine the two directions. The idea is, well, first, although earthquakes happen in all directions for all earthquakes, for lower seismic design categories, the consequences are not so great. And for seismic design category B, you're allowed to still consider the systems independently in the two directions. For higher seismic design categories, if the lateral system elements are intersecting so that they get loaded from both directions, we need to think about that. So for instance, orthogonal directional combinations are required in ASC 722 if we've got torsional irregularities or a non-parallel system irregularity. It's also important that we think about where the displacements might happen. If we have a twisting building, the displacement at the perimeter of the building is not the same as the displacement at the middle of the building. If there's not much twist in the system, it's probably okay to think about story drifts just at the center of mass. But where there's great twisting, there could be greater deformation demands, and you'd need to understand that to make sure that your system is proportioned properly. And so we'd have to think about the drifts at the perimeter. There is an interesting finding from the project. We found that using one method that you might think is precise would help. It makes the problem worse. The big idea with accidental torsion is that we can't predict perfectly how our system is laid out. So there could be some twisting in a system that is nominally doubly symmetric. It could still twist. And so the long used code rule is that we need to consider a 5% offset of the lateral force from the center of mass. You could do that explicitly in a modal analysis by moving the mass around and performing additional modal response spectrum analyses. That sounds like it's more precise, But in fact, what we find, and it wasn't just this project, past projects have found it as well, that you can actually, for some highly irregular torsionally sensitive systems, that method can actually de-amplify the torsional demand and produce collapse potential. So there are some limits that you say you actually have to use a static characterization of accidental torsion in some instances. And I won't go through all of the detailed modeling requirements for nonlinear response history analysis. They're in chapter 16, but for time, we'll move on to our next poll question.
Great. So our next poll is, which linear analysis method produces story shears, overturning moments, and story drifts that are more consistent with anticipated nonlinear dynamic response at the design earthquake level? And I'll tell you, Mike, this has been a popular topic in the Q&A so far.
Okay.
Great. Looks like almost half of the people in the audience have already voted. I will give everyone a few more seconds to consider their responses and get them in. All right, looks like they're starting to level off. So Mike, I'm going to go ahead and close the poll. I'm sharing the results so everyone can see it. And 2/3 of those in the audience voted for the equivalent lateral force procedure, and 1/3 voted for modal response spectrum analysis.
Yes. And so it may fly in the face of your past expectations, but ELF produces results that are more consistent with the envelope demands from a nonlinear dynamic analysis. So, I mean, on one hand, I guess you could say that the framers of that method who developed it initially did a good job when they were trying to do some enveloping. And perhaps we fooled ourselves by doing more complicated analysis with modal response spectrum analysis, thinking that the answers were more accurate, and that's not necessarily the case. The reason being, in part, modal response spectrum analysis is still linear, and when you have an R factor of 5 or 8, the response is definitely not linear, and so the strength matters a lot in a way that the method can't pick up. So ELF does a better job of characterizing the results. It doesn't mean you can't use modal response spectrum analysis. It does give you some insights into the dynamic performance of a building. But the ELF procedure is both more conservative and generally better matches the envelope of results from nonlinear analysis.
Great, thanks, Mike. I'll go ahead and close the poll.
Great. So now we'll move on to some horizontal irregularity design examples. And I will tell you that there are 5 detailed step-by-step design example handouts. We're not going to go step-by-step through them, but I hope you will find them useful in your practice so that you can better understand the specific requirements in ASCE 7 or other documents, as you'll see, so that you can understand how to do your work. So we're going to talk about design examples. We're going to walk through all of the horizontal irregularities in varying levels of sophistication. And in each case, we're going to try to understand what the trigger is, why we're concerned, and how to mitigate it. So this table summarizes the requirements related to horizontal irregularity in ASCE 712. And it identifies the metrics that we have. How do we quantify it? And then as a result of quantifying it, what do we do for the analysis? What do we do for design? And what do we do for detail? So our first irregularity is a torsional stiffness irregularity. The method is unchanged in essence from what has been in previous editions of ASCE 7, that we apply a static force, we compute how much twist there is in the building. ASCE 722 defines a new term. So instead of carrying around delta max over delta average, we've defined that itself as a torsional irregularity ratio. And that TIR is compared to various triggers that provide for additional requirements, whether you're greater than 1.2 or 1.4 or 1.6, indicating that you're more and more irregular torsionally. The reason that we're concerned about torsional response here is that we could get collapse potential at the perimeter because there's so much twisting. and that the three-dimensional orthogonal effects are significant. And if we ignore those effects, we'll have a poor design. What can we do to fix the problem if we identify it? Well, first, we need to make sure we have the right kind of analysis method to find the problem. We need to make sure that we're checking the drift at the perimeter of the building. We need to amplify those torsional responses make sure that our design, which is, remember, with an R factor greater than 1, that means the problems could get worse as it deforms inelastically. So let's amplify the results. Maybe we need to have places where the collectors and diaphragms need to have greater strength in order not to perform badly. We also have a redundancy factor in our document, ASCE 7, and there are places where the twisting performance is so severe that we need to think about using that redundancy factor. And of course, we can mitigate this by reproportioning our lateral system within the bounds of what works for the building program, let's say. Torsional strength irregularity is a new one to ASCE 722. The definition of this is if 75% or more of the strength in one direction is on or to one side of the center of mass, when the system behaves inelastically, you could get an unanticipated twisting in the system. And that could again lead to a collapse problem. It again is an issue where three-dimensional or orthogonal effects matter. So you've got to have the right kind of analysis to find it, think about the performance at the perimeter, and then amplify loads as you need in order to come up with a safe design. So this is our first detailed design example. I think it's 4 or 5 pages in the handout. We're just going to go over a summary of the results. This is a 5-story steel moment frame building in a high seismic area. You see in elevation the layout of the system. And then in plan, you see the layout of the system. You'll notice that the lateral system is offset in the building, so it's not, the center of the lateral system is not at the center of the building. So there is, in the Y direction, up down on the page, there is eccentricity, which you should expect could cause twisting. In the X direction, there is no eccentricity, so you wouldn't expect to see twisting there. So in the design example, we go through and we calculate the torsional irregularity ratio. It's worth noting that we're looking for problems a story at a time. And so we're characterizing this TIR based on story drift, not on the displacement of the building. And so we go through in the example and we identify we apply static loads, and we include accidental torsional effects, either positive or negative. We have to consider both of those. Because there's some inherent torsion in the negative direction, applying the accidental torsion in the same sense is the worst consideration. So in the X direction, we see that things are regular, but in the Y direction, when we have a counterclockwise accidental torsional moment, that amplifies along with the inherent torsion. And we see that we have irregularity in the top 4 stories of the building, with the worst irregularity being in the 3rd story. Because we have an irregularity, we have to do some amplification of the accidental torsion. When we do this calculation, it's based on story displacements, not story drifts. And the idea here is that if you get twisting in an upper story of the building, if the upper story twists, that twist carries down. And so you'll notice in this case that the 3rd story had the worst performance expected. The systems above it go along for the ride, and they twist as well. And so they get amplification factors, even though those stories aren't as bad. So then when we find this irregularity in the design example, what we had to do we had to do 3-dimensional analysis. We have to do orthogonal combinations. We have to amplify the torsion in one direction. In the other direction, it's regular and torsion does not need to be amplified. We do have to think about drifts at the perimeter of the building because the torsional irregularity ratio is greater than 1.4. We have to consider the redundancy factor in the Y direction, but not in the X direction because it's not irregular in that direction. When we have this type of irregularity, it triggers some increased design forces for collectors and diaphragms, and so those are invoked as well. So that detailed example is for the torsional stiffness irregularity. Let's go on to the torsional strength irregularity. We're not going to have a detailed example here. The idea is if more than 75% of the strength in one direction is at or on one side of the center of mass, there's a twisting potential when the system performs inelastically. So you see that in all of these cases. The top left case, it's a U-shaped system. All of the resistance is on one side of the building for the left-right direction. And so we would expect that we could get some twisting if we get yielding. In the bottom case, all of the resistance is at the center of the building in the left-right direction. So again, when the real ground motion that it's experiencing is not perfectly concentric, we could get twisting that we would not have anticipated. So these would be irregular, and we'd have to think about the requirements as outlined in ASC 722. Moving on to the out-of-plane offset irregularity. This is something that you know it when you see it, so you have to look at your system. When you know that you have a system where the vertical elements from a story above do not align with the vertical elements in the story below, you have this irregularity. The concern is that we could get a greater collapse potential because of demands in the diaphragm. How do we fix it? Well, first we need to understand the problem well, so we have to use three-dimensional analysis. We need to think about the stiffness of the diaphragm explicitly. And then there are requirements to amplify with overstrength factors the demands in those key transitions so that we don't precipitate collapse there. And that includes requirements for the diaphragms and connectors at that level. So the requirements are that we amplify the demands in that diaphragm, and that we have collectors and drag struts, let's say, that make the connections work. The ASCE 722 clarifies this requirement because in the prior editions, if you found this condition at one story of a 20-story building, you would have amplified all of the diaphragm forces at every level. And of course, that doesn't address the problem at hand. So ASCE 722 clarifies the scope that it's where the irregularity occurs, the diaphragm forces have to be amplified. For the diaphragm discontinuity irregularity, consider a large opening, let's say. The concern is that we could get something that we didn't anticipate there. We wouldn't understand correctly the distribution of seismic forces, and we could get concentrations of demands at the opening. How do we fix that? Well, we have to think about explicitly the diaphragm stiffness, and then we need to increase some demands where necessary. The diaphragm discontinuity irregularity also occurs where we've got flexible versus rigid systems and abrupt changes in the behavior that we need to think about those stiffnesses explicitly, or we'll miss the real issue. And then we've got, if we change the stiffness of the system, say a very flexible system over a very stiff system, that could produce dynamic results that we would have missed. So we need to think about those explicitly. Similarly with the reentrant corner, if the behavior of this reentrant corner is all the action is in the diaphragm, we would miss that if we model the diaphragm rigidly. We'd have to think about that explicitly in order to understand the problem. And then as a result, we probably end up with some collectors and cords in the diaphragm to resolve those increased demands. The non-parallel system, really, we mentioned before, it's not a structural performance issue. We just have to use a three-dimensional analysis to understand it, and that really is the issue.
And Mike, I'm just going to jump in to say we have about 15 minutes left until we are planning to start the Q&A session.
Okay, thank you. So we're going to step into the vertical irregularity design examples, and we'll need to focus a little more quickly on some things. The big idea, again, is there are triggers in ASCE 722 with resulting requirements for design and detailing and other prohibitions, for instance. In addition to the ASCE 722 configuration items that are addressed, there are configuration irregularities that actually occur in other documents. The moment frame, weak column, strong beam requirements actually occur in the material standards, not in ASCE 7. We mentioned that the weight irregularity was removed. Wall discontinuities for concrete walls are addressed in ACI 318, not in ASCE 7. And we talked about how thinking about gravity-induced lateral demands, that's something we need to do in our analysis, or else the results are suspect. Before we can consider these vertical issues, though, we need to get on the same page on how to calculate story stiffness and story strength. It sounds simple. Those words are simple words, perhaps, but there's a lot of disparity in the way that people might think about those calculations. And ASCE 7 doesn't entirely tell you how to calculate story stiffness or story strength. So our project undertook a careful consideration of this so that we could give you some better direction. And as a result, we suggest that you use what we call the apparent story stiffness method. The idea is, instead of trying to do a whole bunch of hand calcs on stiffnesses of each story, we apply static ELF forces, we tabulate story shears and story drifts, and we consider the apparent story stiffness to be the shear in the story divided by the drift in that story. And that'll help us to quantify the issues. For story strength, it could be a really complicated thing where you're doing limit analyses and you're doing nonlinear analysis by hand or another method. That's not the intention of ASCE 7, and the commentary clarifies that. We really just want to have a simple measure, either elastic or plastic, to understand how the strength varies in a building. And so a couple of examples, if we're looking at braced frames, we have a number of things that could control. It could be brace buckling in compression. It could be brace yielding in tension. It could be uplift of a foundation system. It could be yielding of a connection. And those are pretty complicated endeavors, but we can work through what is the controlling set of capacities and describe that as the story strength. With moment frames, again, we've got shear capacities in columns, we've got flexural capacities in columns, flexural capacities in beams, and you could think about all of those things. Again, the idea is to consider the various behaviors and find what controls, what has the least strength for the story, and that's how you would characterize the story strength. For shear walls, similarly, wall piers, we could think about shear response and flexural response in order to then characterize the story strength. So let's talk about our irregularities. And the document P2012 gives a lot more detail on the strength calculations and the stiffness calculations. And those are necessary to do the metrics. So if we have a weak story irregularity, we need to be comparing story strengths. The concern is that at the weak story, we could get inelastic response that is concentrated and the system could collapse. So then we need to think about what to do. We could strengthen the weak story. Possibly you could weaken the stories above so that you don't get the demand concentrated there. And this type of irregularity has both an irregularity and an extreme irregularity with some different requirements depending on the severity. Detailed example 2 in your handouts is for a 3-story shear wall building with an opening at the 2nd story. And we work through calculations, which I won't go into in detail, but we considered carefully story shears and we distribute those forces. We look at the behavior of each of the piers in the 2nd story so that we can understand the shear and flexural strengths of that story and compare those to the demands. In the case of this example, minimum reinforcement works in this wall, except at the 2nd story where we have to have some piers that are reinforced more heavily. And what we find is that when we calculate story strengths, we calculate the story strength of the 2nd story, thinking about both of those piers and their controlling behaviors. Shear controls, not surprisingly, over flexure. In the 3rd story, we have shear, and what we find as a result is that the 2nd story has only half the strength of the story above. That means that not only is it a weak story, it's an extremely weak story. That would be prohibited in high seismic areas. And it's even prohibited in seismic design category B or C generally. Now, with our calculations show that all of the DCRs are less than 1. So the design, quote, works, but it misses an important aspect of configuration of the weak story. To mitigate it, we need to strengthen that story. We talk about that in the example. You could strengthen it just enough so that it's not an extreme irregularity, but it's just irregular. That's not recommended, even though it may be permitted to have a weak story irregularity as long as it's not extreme. If you're going to improve the system, make it just a bit stronger and eliminate the irregularity completely. For the soft story irregularity, we're looking for dynamic response, so being concentrated in a story. The idea that we could get a concentration of demands there that could be problematic. And so we go through a steel moment frame example, detailed example 3, and cutting to the chase, we find that for this system with pinned bases at the columns, we have an extremely soft story at the bottom. The way we mitigate that is by introducing grade beams to connect the columns at their base. And that eliminates that soft story concern, makes the building perform regularly. In plane discontinuities, you can expect that the column in red here is going to see much greater demands than your R=5 analysis would suggest. And so the concern is that if that column fails, the whole system fails and we have collapse. And so we're required to amplify the design forces in the element that's supporting those discontinuous forces. And we also need to think about the diaphragm forces and amplify them at the level where the irregularity is introduced. For the weak column, strong beam irregularity, the concern is that we could actually get little mechanisms in the columns at a story and cause the story to collapse. This is not addressed directly in ASCE 7. Instead, it's addressed in the material standards. And so we have a design example for each. Design example 4 is for a concrete moment frame where we identify an irregularity because the columns are not strong enough to satisfy the requirement that's in ACI 318. And as a result, we need to increase the strength of the column so that we don't get that possible inelastic response. We strengthen the columns and the system works. Detailed example 5 is the same idea, but for a steel moment frame, and all the detail is in the handout. The vertical geometric irregularity that we spoke of earlier, this is really, you see it is quantified in that you're measuring the lateral force resisting system elements, but the concern is qualitative, that if there's too big a change, it might cause poor performance at the irregularity. What's worth noting here is that the concern is the size of the seismic force resisting elements, not the size of the building. So on the left-hand side, the step back is small enough that it's not irregular. On the right, it is irregular because the system above is only half the dimension of the system below. In this example, there's no irregularity in the seismic system. The building massing changes, but that does not trigger the irregularity. It's a concern with the strength and stiffness of the actual system, seismic system. We mentioned the weight irregularity has been eliminated because we have to model the mass correctly. And if we do follow all of the requirements in ASCE 722, our design will be adequate. And then wall discontinuities are not addressed in ASCE 7, but various aspects are addressed in ACI 318. The concern is that at those discontinuities, we could get increased damage, and maybe in some cases, as you see at the bottom, with a really big opening, there could even be collapse. I'll note that that also qualifies as an in-plane discontinuity. So ACI 318 tells us how to consider the effective flange dimensions. So when you're at the very top of this, the red area in this wall, you can't assume that all of the wall reinforcement is participating because there's a shear lag effect. And so we have to think about the effective flanges. Similarly, where we have a wall pier, ACI 318 has definitions of, is it a wall segment or a wall pier, or is it a column? and how do we approach the design. And then at panel zones at the top and bottom of a stack of openings, we can get a concentration of damage. And there are requirements. It's addressed a little bit in ACI 318, this panel zone idea. The references here in Jack Maley's book that gives you a little bit of some design suggestions on how to deal with it. And finally, the gravity-induced lateral demand. The concern is you could exhaust some or all of your lateral capacity just due to gravity loading and not be ready for lateral loads that are applied if you didn't consider the effects the gravity loads have on the lateral system. So please do consider it. And that concludes the presentation portion. I think Kiara is going to lead us into questions and answers.
Mike, you really picked up the pace at the end.
I'm sorry I had to do that, but I think they have the handouts and the detailed examples. The way they really benefit is by going step by step through them on their own projects.
And Mike, that's totally fine. We have tons of questions that we can start going through. I was just still reading through the questions and trying to organize them. So great. So I think just before we dive into the Q&A session, we'll just touch on PDH certificates, which is always a popular topic amongst participants. So just note that if you are watching this live and you're registered under your name, you will receive a PDH certificate automatically via email within 4 weeks. If you're watching the recording, you're not eligible for a PDH certificate. And just please be mindful that we cannot make exceptions to our PDH policy due to the large volume of participants on these webinars. And then in terms of the Q&A, we've gotten a ton of great questions. We'll be able to get through some of them before the webinar end time. If we don't get to your question, I will be sending all of the written questions we received to Mike after the event. Right now, I'm going to say that I think we've received too many for him to respond to all of them, but he will respond to a subset of them and we'll get them out to you via email within the next 4 weeks. So with that, Mike, I think we're ready to dive into the Q&A. Are you ready? Or do you want to take a deep breath? Drink some water. All right, so I have tried to organize the questions we received into topic areas because I think there are a few topic areas that definitely came up a lot. The first one is the gravity-induced lateral demands. So there was a lot of interest in why they're not being addressed in ASCE 722. I think you had a slide about how there was a recommendation about it in P 2012 and it wasn't incorporated into the standard. So if you can speak to that. And then I think some people just had they wanted a little bit more clarity about what it really means in practical terms to have gravity-induced lateral demands. So I think there was a lot of interest in the topic. So maybe just expanding on it a little bit and speaking to why the recommendations weren't integrated into the standard and if they would be in the future.
Sure. So is it good or bad if I were to go back one slide to have that gravity-induced lateral demand is on that slide?
I think it's great.
Okay. So first, how do you, on the practical side, how do you know if you have this? Well, I work with architects a lot, and many of my architects, whether it's for programming reasons or for architectural expression, they might like a sloping column, or they might like a step in the location of a column from one level to another. As a result, the gravity loads have an inclination in plan. And that means that there is a shear that results in the building as a result of it. In the case of this simple cartoon, all of the weight above the red columns is at one location in plan, and that same force has to be at a different location in plan below. And so there's a horizontal shear that resolves into the system. And that shear has to be resolved in the lateral system because that's the source of lateral strength and stiffness. So even if there's a single sloping column, there are thrusts induced in the system that should be considered. So that's the behavior, that's the background of why it's a concern. I wish that the change had been made in ASCE 7. You could argue, some could argue, and perhaps some did at the committee, that since we already have to explicitly think about the strength and stiffness of a system, this should be in any good analysis. I believe that the effect is missed by some, especially if they separate their gravity analysis from their lateral analysis. And because if they separate those two and they're unaware of this situation, then they may be under designing. So one way you could know you have this issue is if you go ahead and you model the sloping columns in your lateral analysis model, and don't even apply earthquake or wind loads, just turn on gravity, and you'll find that you get some story drift and you get some story shear in the system. And that's just due to the application of gravity. If that's the case, if you are correctly looking at your building, its real layout, and you get lateral forces as a result of vertical loads being applied, the effect is important and should be considered. And if you ignore it, you're ignoring some of the lateral forces that are occurring in your building, and you're unconservative.
Great, thanks, Mike. I think that answered many of the questions we've received about the gravity-induced lateral demands. Okay, so next, I think we do need to talk a little bit more about ELF versus the modal analysis, because I think that was a lot of people are I think, very interested in the finding from P 2012 and the implications on ASE 722. So I think, is there anything you can comment about why you would want to use the modal analysis? So in what particular cases you'd want to be using it, understanding the findings from P 2012. And there's also been a couple questions about the limitations on using ELF for buildings of a certain height. It says for above 48 meters, and whether there's any anticipated change coming out of the P 2012 findings that might affect the ability to use it for taller buildings.
Sure. Okay. So let's talk about low and mid-rise buildings for a minute, where the standard would allow the use of either method. I will say in my practice, my practice in the last 12 years has been definitely weighted toward high-rise construction. And so for high-rise work, we always use dynamic methods of analysis, so modal response spectrum analysis and nonlinear response history analysis or linear response history analysis, because the dynamic behavior of a tall building is different from that of a short building. So for short buildings, for the ELF method in general, the idea is that we get an inverted triangular acceleration profile that is intended not to be true or correct, but it's intended to envelope story shears and story moments and story drifts. And it does a good job of enveloping those things. It may go too far sometimes. In other words, if I have a 1,000-foot tall building, the loading really is quite different from the ELF loading, the actual anticipated loading. And a modal response spectrum analysis can help me to identify some of those dynamic characteristics that I believe are important for my system, instead of overly penalizing all of the system. So turning this around, the challenge we had was there were a series of irregularities where the implication to design was you're not allowed to do ELF, you have to do modal analysis if you have this irregularity. And the difficulty there is we were requiring people to use the modal analysis method. And when we did those designs, we found that some of those designs with the modal method actually had worse collapse performance than the methods from ELF. So the conservatism of the ELF helped the system out. And it's unlikely that code writers are going to prohibit the use of modal response spectrum analysis, of a more complex form of analysis. But we certainly shouldn't prohibit the simple conservative method. That was the idea. For high-rise construction, so very tall construction, there is much to be gained from considering the dynamic response of the system. And so there still are triggers for modal analysis for high-rise construction, for tall structures, because that dynamic character is quite different from the simple characteristics identified in ELF. So I'm not trying to suggest that all systems should be designed ELF, but you should know that if you design a short building using the modal response spectrum analysis method, there may be behaviors that you don't pick up because it's a linear analysis, and ELF would have covered a lot of those problems.
Great, thanks, Mike. It seems like that's a really important takeaway from P 2012. Okay, then we have a couple of questions. There are a couple of questions that are related to torsional irregularities. So a few people were wondering some variation of this question. Do you still have to design for the irregularity if the story drifts are overall very small because the stiffness, the system isn't inherently very stiff? So I think that was a question that a few people had.
Yes. Yeah, and it's a question I run into all the time. So the answer is yes. We are normalizing those displacements. So it's the TIR is delta max over delta average. And so it doesn't matter if the delta max is 1 inch or 1/4 of an inch. If its relationship to the average satisfies that trigger, there is twisting in the system. I will say that so it's a mathematical reality that there is twist in the system. Is the twist important or does it cause damage? That's a different question. And so I would say where this really comes into play is in ASCE 716 and earlier editions. There were times that having the torsional irregularity, the system was prohibited if the TIR was too great. And the problem with that is that if you have a system that only has 1/4 of an inch of displacement in a story, but the average is 1/8, that rotation is triggering a torsional irregularity, and the system is not permitted at all. And so the prohibition on the system was eliminated in ASCE 722. So you're allowed to have that torsional response. You still have to go through the calculations. And so it eliminates that big hammer that was a problem because it's non-dimensionalized.
Great, thanks, Mike. So we have a couple more minutes. Let's see if we can do 1 or 2 more questions. Somebody wanted to know if there are certain irregularities that are more susceptible to longer duration motions versus shorter duration motions.
Yeah, I mean, I think all of our inelastic response can be affected. I live in the Pacific Northwest. I live in Seattle, and we have subduction zone sources off the coast. And the reality is, for very tall structures, we could expect that 3 minutes of shaking at a large displacement, the number of cycles could cause poor performance as compared to a closer earthquake that had only 1 or 2 cycles of inelastic response. That's probably generally true, regardless of irregularities. But probably story weakness or story flexibility. So weak story or soft story, perhaps those are most susceptible to some duration effects. The strong column, weak beam rule is important. If you have lots of cycles of inelastic response at a joint, it would tend to deteriorate. And so any of those that we identified as collapse concerns may well be worsened by long duration and multiple cycles.
Great, thanks, Mike. All right, let's see if we can squeeze 1 more in. So this one is for a reentrant corner type diaphragm. It used to be a 15% projection, but now it has been increased to a 20%. What is the rationale behind this change? And one of the reasons I picked out this question is because there are quite a few questions we received, which is like, they were like, in the Canadian codes, it uses 10% for accidental torsion, and we use 5. What's the difference? So maybe just speaking to like how these numbers evolve and how they change over time.
Sure. So that one and another one, the triggering dimensions for the diaphragm irregularity were adjusted. And I mentioned this was not the result of lots of reentrant corner diaphragm calculations. Instead, just like the original codification, it was some judgment. I will say that the original metrics that are in ASCE 716 and earlier actually trace their origin to ATC3. So ATC3 project. This was the ATC 123 project, and they number them. So the ATC3 project sought to bring us into a new world of structural engineering as related to earthquake performance. And there were concerns about irregularities. They were quantified, there were graphics drawn, there was voting on it. And at some point, when that was translated into the NERP recommended provisions, some adjustments were made, and we think there was not a good reason to make those adjustments. So we as our project looked at it, and then also ASCE 7 Seismic Committee readdressed the issue. And the dimensions that are in ASCE 722 are more consistent with what we anticipated when first formulating these irregularities 40 years ago.
All right, thanks, Mike. So I think we're a little bit past now, so that would be our last question. So just before we close the webinar, I'll just say a couple final words. There is a survey link that pops up when you leave the webinar. We really, really appreciate you responding to that survey, because there's one section where we ask you to say which topics are of interest for future webinars, and we look at that really closely to decide our webinar program for the future. And you will expect a follow-up email in the next day or two that will include a link to the recording, which will be up on our ATC YouTube page. It'll also include another link to the handouts and the survey again. So with that, on behalf of FEMA and the Applied Technology Council, I would just like to thank Mike for his presentation. It was excellent. We got a ton of great questions and a lot of interest in this topic. And I'd like to thank everyone in the audience for joining today. And this concludes the webinar. Thank you.